Okay, time for part 3 of hydrostatic pressure in calculus. Now, I left off part 2 with this problem, and this is the one ultimately I want to do in the video, but given that this porthole that we're dealing with here is circular, then we need to talk about just the kind of equation that we use to track all the points on a circle. Okay, because that's the way that we set things up. Like, we need formulas and equations. As I told you, that this is, no matter how the situation is described to us, we conceive that there's some shape in a fluid, and everything that is involved is a function of y. All right, if you follow my setup. I'm not saying that this is the only way to set it up, but if you follow what I'm doing and what most other people would show you, then that's the way it is. So we're going to need some equation for this. So let's hold off on that and just talk about circles and their equations. Okay, so let's conceive of this. So suppose we got a circle and it has a radius of r, whatever that is, and a center at the origin. Okay, then the equation of that entire circle and an equation that would satisfy every single point on it with their x and y coordinates would be the x coordinate squared plus the y coordinate squared is equal to r squared. If this is a point on that circle, that's what the x and y coordinates are guaranteed to do. This equation will always be true. Now, you might not want to deal with the entire circle. Maybe you want just the top part, or maybe you want just the right-hand side, or something like that, okay? So if we solve this equation for x and y in different ways, we would find that the top portion is y is equal to root r squared minus x squared. The right-hand side only is x equals to root r squared minus y squared. Okay? All right. So y is r squared minus x squared. Solve for y, positive root, you get the top. From this, x equals root r squared minus y squared. Solve for x, positive root, you get the right side. Now, whenever you solve this, like whether you're going to solve this for x or y, say you're going to solve it for x. X is equal to, let's say x squared is equal to r squared minus y squared. That's probably your first move if you're going to solve it for x. And then how do you solve for the square? Well, you take plus or minus root, okay? So if you're truly going to solve it for x, then it's going to look like that. But given that you could take either the positive or the negative root, do you see why the positive root gets you the right-hand side, where the x coordinates are all positive, and the negative root would get you the left-hand side, where the x coordinates are all negative, okay? So if I want just the right-hand side, it'll be the positive root. If I want the left-hand side over here, then all of those points would satisfy the equation x equals negative root r squared minus y squared. Okay, let's look at an example. Why not? Examples usually help. So suppose I have this circle, all right? So imagine that there's a whole circle there, and it has a radius of 1, and that's something that you can figure out because of these points I labeled on it. We're all at 1 on the x-axis, 1 on the y-axis, and so on. And suppose I tell you, like based on what I showed you in the last slide, that the equation for only the right half would be x is equal to positive root 1 minus y squared. The radius is 1, okay? How do you get that? Well, take the equation for the circle, having a radius of 1, x squared plus y squared is 1. Solve for x, positive root gets you the right half, negative root gets you the left half. Okay, so there's your equation for just this, okay? Now, what do I mean by saying, well, this is the equation for that semicircle, right of the y-axis? All right, given that I'm putting this circle right here with its center at the origin. How does this equation, what do we say, or what do we mean when we say this equation is for that? It all comes down to points, you know? If you take the x and y coordinate for any point on that semicircle, it will work in this equation. It will reduce the equation to a true statement. That's what we're saying. And if you took some point that wasn't on that right semicircle right there, it wouldn't work in the equation. It would produce a false statement. In math, you can always try things out, see if they work. If you have trouble understanding something, try it out, see if it works. Put numbers in, start doing calculations. So here's 2 points are on the right half. Okay, and these points really are on the right half of that circle. I promise you they're on there. If you took 0 and -1 and you put 0 for x, -1 for y, you would reduce to a true statement. It would say 0 equals 0. True, it works in the equation. If you took this point, 1/2 for x, -√3/2 for y, and you put it in that equation, this equation right here, it would also reduce to a true statement. 1/2 is equal to the positive root of 1/4. It's true. That's how this equation, that's what it has to do with this geometric shape, okay? And that's true for any equation versus any shape. Line, circle, ellipse, whatever it is. That's what we mean. Just for comparison, take this point right here. It's not on the right half of the circle. It's not over here. -1/2 for x, -√3/2 for y. Put it in this equation. It shouldn't work, and it doesn't work. It reduces to -1/2 is the positive root of 1/4. That's not true. -1/2 is not equal to 1/2. So that's, a lot of detail for why this is the equation of that. I decided to give a lot of detail because I don't normally go into a lot of detail on that sort of thing, so I thought it would be time. So let's do this. Let's do the problem with the water pressure on the porthole of the submarine, but let's do one other one before it where the math is somewhat intricate. All right, so imagine this situation. Okay, imagine this in the context of what I had just told you about circles, and imagine it in the context of what we talked about in parts 1 and parts 2. Okay, so imagine that there's this weirdly shaped plate that's like half triangle, quarter circle, all right, combined together. But it's some plate, it's flat, it's vertically submerged in water. The water happens to be 2 feet above it, okay? And because it's in water, there's pressure on the plate, and our question is, what is the force of the water, the total force of the water on one side of the plate, okay? Or if you thought, well, this is some like crazy looking car door, what's the force of the water on the door? All right, one side of the door, the part that's exposed to the water. So this plate is flat and it's submerged vertically in water. Now, the numbers that are given are that, all right, the very top of this thing is 2 feet deep, 2 feet under the water level. This triangle has a 45-degree angle there, 90 degrees here. As a result, it's also 45 over here. The hypotenuse is 1 foot. And then this is a quarter circle, and there's no dimensions given at all. Okay? So first with the triangle, let's do a little bit of analysis on the triangle. Isn't it, well, okay, so it's 45 degrees, right? And I know the hypotenuse is 1 foot. All right, sure. I could use lots of things. I could use the proportions for a 45-90 triangle. I can use sine and cosine. But nonetheless, like I can figure out that this side and this side have a measurement of 1/√2 feet. Okay? All right. So they end up being the same because these angles are the same. But if you use sine or cosine to solve for either of them or both, they're each going to be 1/√2. So this triangle right here is 1/√2 feet like this and 1/√2 feet like that. Well, that tells us the size of that circle, doesn't it? This is a quarter of a circle, right? But that would be the center right there. And this would be the radius, or this would be the radius. Now, I know that now. I just figured out this number. The base of that triangle is 1/√2. So that quarter circle is a quarter of a circle that has a radius of 1/√2 feet, okay? So let's do this. In order to keep with our method and impose the y-axis on our situation where the fluid and the surface are in contact with each other. All right, I'm going to do it like this. I'm going to take this surface, I'm going to put it like so. Okay, so here's the water level, there's the surface. So equations. All right, let's think about the equations. Now remember how I found the base and the height of the triangle, and I said it was 1 over root 2? That makes, if I put that plate where this is the origin right here, okay, that's the origin, that makes this a distance of 1 over root 2, so that's the x-coordinate, the y-coordinate 0, it's on the x-axis, and that makes this 0 for x, 1 over root 2 for y. All right, so that line right there, which gives me the width of this plate. Now remember, we need to know the width up and down the y-axis. Well, the line, the equation of that line through these points is y equals negative x plus 1 over root 2. But solving it for x and doubling that gives you the width. Okay? Or, sorry, we don't need to, look at me. Do we need to double that this time? Let's see. Isn't it just that the x-coordinate alone tells you how wide? Oh, yeah, we don't need to double that. We don't need to double it at all. Okay, now what about the circle? Okay, well, so for the circle, that would be like the lower portion of the right half. Okay, so the right, if I had this whole circle right here, then the right half would be x equals root r squared minus y squared. Remember, so we talked about that just a minute ago. If the radius is 1 over root 2, then r squared is 1/2. So the right half is x is equal to root 1/2 minus y squared. So that tells you, like the x right there tells you what? When I say x equals, what's x? X is horizontal on a graph. X is left and right. So that tells you the width among the circular portion. So this tells you the width among the triangular portion. And this tells you the width along the circular portion. So here's the difficulty with this problem. It looks like I have everything I need. Okay. Oh, one more thing. Where do I put the water level? Let's see. Is 2 feet above the top? Okay. So where's the top? Right there. All right. And what's the y-coordinate? 1 over root 2. So where does that need to be if this is 2 feet above? Well, 2 plus whatever the y-coordinate is for the top. Well, that's 1 over root 2. So the water level is at 2 plus 1 over root 2. So here's what I've got then. In our setup that we learned earlier, once we get our situation imposed on the y-axis, I need the width and depth in my integral, okay, as functions of y. And the difficulty with this one is there's not one function, there's not one formula that gives you the width all the way through this thing. Because part of it's a line and part of it's a curve. Part of it's a triangle and part of it's a circle. So the width is 1 over root 2 minus y for the triangle. The width, though, is root 1/2 minus y squared for the circle. So there's not just one formula. So that means because of that, we're going to need 2 integrals. And we'll just have to say, well, here's the pressure along the triangular portion and the total force that results. We'll get that number. And then here's the total force that's on the circular portion. And we'll get that number. We'll add them together. But since there's not one formula for the width, there's not going to be one integral. Okay? All right. Now what about the depth, though? Does this give you the depth like anywhere along the y-axis? Well, yeah. If you always just take where the water is and you subtract y, then that will give you the depth everywhere. Okay? Like right here, like how deep is that bottom part of the circle? It's going to be, well, this is at 2 plus 1 over root 2. You subtract the y-coordinate. So that's going to be 2 plus 1 over root 2 minus negative 1 over root 2. So you're subtracting a negative, you end up adding for these parts. But if you subtract whatever the y-coordinate is all the way along, it does tell you the depth with respect to the water level. Okay, and that's what we want it to do. Okay, so the depth might be the same through the whole shape, but the width isn't. Now, okay, with that out of the way, with me hoping to convince you that you need two integrals, here they are. Okay, this is the one for the triangle. All right, we got our weight density. Okay, we've got our width, depth, dy. The triangular portion spans from 0 to 1 over root 2 on the y-axis. There's our integral. And then this part is the circular portion. The circular portion spanned the y-axis. What was it? When I took this, put it down on the xy plane like that, the circular portion spanned the y-axis from negative 1 over root 2 to 0. So I go like that for my bounds. Weight density, width, depth, dy. Okay? Now, for both of these integrals, I actually used Wolfram to solve them. And I'm going to put a note in our assignment and on our test that if you want to use your calculator or an online calculator that solves integrals, definite integrals for you, you can use that. You don't have to do this one or that one on paper. It would be hard to do. It would be very time consuming. And with such problems as this, I'm more concerned that you understand how to set them up anyway. Okay? So as you're watching the video, just be prepared that on the assignment, there's going to be a note that says it's okay to use whatever kind of calculator or online resource you want to evaluate the definite integrals. Okay? Nonetheless, there's two of them. I saw both of them that way, and the total force on that plate is 112.24 pounds. Okay? All right, so let's do our last problem, okay, for this lesson. And by lesson, I mean that we have a flat vertical surface that's in contact with fluid, and we aim to calculate the force on that surface as a result of the fluid and the pressure within the fluid. Here's the last problem that I'll show you for that lesson. So suppose we have a submarine, okay, that happens to be underwater like so. There's a porthole on the submarine. It's circular, it's vertical, and implied in me telling you it's circular is that it's flat, okay? The top of the porthole, which is circular, is 17.5 feet beneath the surface, okay? The radius is 1/2 foot. Here we're in the ocean, so that's salt water, which is a little bit more dense than pure water, so it's 64 pounds per cubic foot. All right, so that's the number we're going to use for the weight density. Can you calculate the fluid force on the porthole? The water's pushing in on the porthole, right? Like keeping it shut. All right. I don't know anything about submarines. I doubt it would open anyway, but the water's pushing in on it. Okay. How strongly? All right. So this is kind of like that example with the car door being underwater. It's just that this is further underwater and it's a different shape. Okay, so let's think about how we would do that. Now remember, I need to take this, whatever this is, there's an object underwater, and so on and so forth, and I need to impose the y-axis on it like that. And there's lots of different ways you can do this. As I make the video, I choose a certain way to put the y-axis on my situation. It's not the only way. You could do it different ways. If somebody else showed you, they might do it slightly differently. As long as you're consistent, like as long as everything you come up with is accurate, as long as it really does span from A to B, and those are the right numbers, and as long as your width equation is accurate, and your depth equation is accurate, as long as all that's true, then it doesn't really matter how you do it. But here's how I decided to do it. So we're just talking about the porthole and the force of the water on that. So I put it like this. I drew the porthole as a circle with the center at the origin. Okay, so here's the x-axis and here's the y-axis. And I did it like that because I know that I'm going to need an equation for that. Okay. Why? Well, because that's how you find the width. All right. Part of what we need is the width of this shape all the way through it. So I wanted this in a way that the equation was easy to get, so I put the center at the origin. Now, if the radius is half of a foot, then that would make, like, say, this point right here, 0 for x, 0.5 for y. And that would make this point over here, 0 for x, negative 0.5 for y. Where would I put the water, though? Well, so in our picture, it said that the top of the porthole is 17.5 feet underwater, okay? So that means, like, from here, if we're decisive about how we want the circle to be on here, from here to here needs to be 17.5 feet. Well, if this is half a foot and then you go 17.5 feet up, that puts the water at 18. Okay, so the y coordinate for the water level is 18. Now, let's see about the circle. Imagine if we got, since we talked about this, let's say, okay. Imagine if we got an equation for just the right-hand side. Since we know how to do that, that would be x equals positive root r squared minus y squared. So the radius is 0.5, 0.5 squared is 0.25. So x equals root 0.25 minus y squared. So that just gets you this. Now, a minute ago, we were doing a problem, and I said, well, we got the width, we need to double it. And I was mistaken on that problem. There was just this. There wasn't a side over there, okay? This time, if that x is equal to root 0.25 minus y squared, if that gets you the right half, that will get you, like, all these points. If I were to double the x coordinate of any of these points, that would be the width all the way across, and that's what we need. This porthole is an entire circle, not a half circle, okay? So I'll find the equation for the right half, and I'll double it, and that will be the width. What about the depth all along the y-axis? What's the depth? Well, the water is at coordinate y equals 18. 18 minus y tells you the depth wherever you are, okay? Like this point right here, how deep is that point? 18 minus negative 0.5, okay? So in other words, it's 18.5 feet beneath the water, and that would be true, right, on our situation. Where's the bottom of that porthole? Well, it's got a diameter of 1 since it has a radius of a half, and it's 17.5 feet to the top, so it's 18.5 feet to the bottom. Yeah, this gives us the right number, okay? Remember, all I said is however you set it up, these have to be accurate, and they both are here. All right, now that's going to be the hardest part when you do these. Once you figure out truthful equations for the depth and the width, we have our integral. The object this time spans the y-axis from negative 0.5 to positive 0.5, okay? And then I put weight density times depth times width. That's how I got that constant from the 2 and the 64. And then you see the rest of it, okay? I did this integral also with Wolfram, right? You can do that. You can use an online resource or calculator of your choosing to do the integrals. I just want to see that you set them up. It turns out to be a net force on the portal, at this depth at least, of a little more than 900 pounds.